Okay, let's talk a little bit about voltage fields and potential energy. This is an area that I often find that even though we've done a lot on these things, students don't really understand because we don't really tie it all together that well. So this is hopefully what my little video is going to do. What is voltage? Let's write down a few of the things we've found out over the years. We've had that formula, voltage is energy per charge. That's a good way of looking at it. We had that formula that voltage is the electric field times the distance you travel in it. That's very important to remember that one. We've said that force is equal to the electric field times the charge that's in the electric field. That's the charge it experiences, the force it experiences, sorry. So based on that, we could actually say that the voltage is equal to, remember that was electric field, sorry. The voltage is equal to the force divided by Q times D. So this ties up with our first equation. Force times distance is work or energy divided by Q. Those equations are nice. Another little analogy I like to use with my students is the analogy of potential energy. If we've got an object and it goes from this height to this height, we say mgh equals energy. Now we could say, well, what's the energy per mass, per kilogram, if you like? Divide by mass, and we've got a new unit, gers, or GHs, ger. That's kind of like what voltage is. It's energy per charge. We give it a special name with electricity. We don't give it a special name with electricity. So now we've had a little look at that. Let's have a look at a charge. Get a big positive charge. We know the electric field goes from plus to minus. We could go in any direction we like, but originates on a positive charge, and that's the electric field. So I put a little line underneath my E so you're clear that it's not energy, that it is the electric field. We just said in the electric field over in this formula, if you go a certain distance, you've changed voltage. So if these guys are at the same voltage and you go a certain distance, then that's a change in voltage. You can keep going further and further and further and further away, and you get different voltages. Voltages are going to decrease. So if we start off at a very high voltage, we'd expect by the time we get to infinity that we'd be at zero. So we define the voltage at infinity, define voltage at infinity is equal to zero. Starts to make some sense. So if these are all positive voltages, then I'll be getting smaller, 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 all the way to infinity. And that is in fact what happens. Let's just do a little bit more on this and see where it takes us. Now, we need to know about Coulomb's force law. Just like the gravitational force law, except it's the force between two charges instead of two masses, and it's a much bigger force. So the force is equal to K, Coulomb's constant, Q1 and Q2, all over R squared. Similar to the gravity one. So if you've got two charges, one here, the forces are going to be equal and opposite. Right? Obviously, that's a positive and a negative charge. Doesn't matter which way around. That one should be a little bit longer because they are equal and opposite. Because you've got that force of attraction. If you'd had a positive and a positive, or a negative and a negative, it would have gone like this, right? Coulomb's force law. But we said that the force equals EQ. So if we divide by Q, if we call that maybe that Q2 a positive charge, so if we divide by Q2, and just call that a normal positive charge, 1 Coulomb of positive charge, then we can actually say that the electric field is equal to K Q1 over R squared. The electric field from our charge. So this could be our Q1 if you like, the positive charge over here. And that's our electric field. So we've got a formula for our electric field there. Nice. If we now want to know the voltage change, all we need to do is multiply that by distance. So we multiply that whole thing by distance, and we've got the change in volts. So change in volts equals E times D. We'll find out that we actually need to say change in volts equals minus ED. That's just so that all the signs work out, so that the energies work out, everything else works out nicely. So we're getting a bit closer. The problem is, to work this all out, the electric field's changing. So you know that when you've got a function showing the electric field and it changes over root squared, that's going to be an integral you're going to have to do if you're going to work this out. So if we wanted to work out the voltage at a certain point, So calculate voltage at point R. It's kind of like I'm saying, we've got a charge here, we've called it Q1 if you like. We're saying, out this distance, what's the voltage there? We know the electric field, this is it here. So what does it mean by what's the voltage there? Can there be an absolute voltage? Yes, there can, because we keep saying all the time, well, voltage is just this difference, and there's not an absolute voltage, just like there's not an absolute height. But there is. We didn't talk about an absolute grr, because we don't use the word grr. But what if we said, well, what's the voltage between infinity and that point there? All we'd have to do is our integral between R and infinity for E, which is K, Q1, because that's Q1, all divided by R squared, times dr. And when we've done that integral, we'll come up with it being equal to K Q1 all over R. And that's our voltage, believe it or not. And the only thing that gets a little messy here, but you can figure it out when you do it, is the negatives and positives. But the voltage for a positive charge ends up being a positive voltage. So what we end up over here is we get positive voltages. So from a positive charge, all the voltages out to zero are positive voltages. Positive voltage. It's all exactly the same for a negative charge, except they're all negative voltages, all going out to zero as we get to infinity. So that's the voltage. So we've got voltage, electric fields, potential energy. What's potential energy? Well, the potential energy is just the energy per charge at that point. So, sorry, the voltage is the energy per charge at that point. So the energy is equal to the voltage times the charge you've put there. This is the Q2 now. So potential energy is just going to be equal to the voltage times the charge. We just said the voltage here was equal to K Q1 over R. Now that KQ1, that's the voltage produced by that charge, which we said if it's a positive charge, it must be a positive voltage. And to get the energy, we just multiply it by Q2, which is the charge you put there. So Q1 is the charge that produces it. So it's like Q1 produces this voltage here. Then you put Q2 there, and it's actually got a potential energy that is equal to that. So depending on whether you've got a negative voltage there or a positive voltage there, and depending on whether you bring a negative charge or a positive charge, your energy is negative or positive. And you don't even have to worry about negatives, because you can always know that if you're bringing a positive charge towards a positive charge, you're going against the force. That's a positive energy. If it was a negative to a positive, it would have been a negative energy. You might have to watch this video a couple of times, but that's it in a nutshell.